Every single day, humanity generates petabytes of raw data. It is a volume of information so massive that it has entirely eclipsed the processing limits of the biological human brain. To navigate this flood of information, we had to engineer a bottleneck bypass. Artificial intelligence allows machines to simulate human problem-solving and comprehension, scaling those abilities to meet the demands of a digital world. The engine driving this simulation is machine learning. Instead of hard-coding rigid rules for every possible scenario, we feed a system raw data and allow it to independently identify the hidden patterns. This transition from manual analysis to algorithmic processing is what allows us to maintain control over a data landscape that has grown too large to navigate by hand. Beneath the surface illusion of intelligence, the entire system rests on a bedrock of pure mathematics. Look at this 3D coordinate space. By applying linear algebra, we take hundreds of chaotic data points and organize them. A regression equation draws a line straight through the chaos. Instantly, random dots align into a predictable trajectory. That simple calculation provides the initial spark, proving that even the most chaotic global data contains predictable truths just waiting to be extracted. Theoretical math is useless if you cannot process the raw material at an industrial scale. That is where Python comes in. It serves as the foundational programming language, acting as the heavy machinery for the entire AI industry. Because real-world data is incredibly messy, we rely on specific tools within Python, like the pandas library, to ingest unformatted text and numbers, clean them, and funnel them into a functional pipeline of rigid rows and columns. If these data pipelines aren't meticulously structured from the start, the most sophisticated mathematical algorithms in the world will simply collapse under the weight of the noise. Once the data is organized, we can train the system using supervised learning. We feed the machine thousands of historical examples where the outcome is already known, providing a foundation of ground truth data for the system to study. This 2D graph compares house sizes to their prices. Using linear regression, the machine calculates a line of best fit through the historical data, extending that line outward to predict a continuous quantity, like the price of a house that hasn't been built yet. If we need to make a strict binary choice, like predicting yes or no, we use logistic regression. The straight line warps into a rigid S-curve, cleanly dividing the data points into two distinct zones. These regression algorithms are the exact mechanisms that grant a machine the ability to analyze a situation and make a definitive choice. To verify the machine actually learned something, instead of just repeating what it was shown, data scientists take the total dataset and slice it into two pieces, an 80% training block and a 20% testing block. The system is built entirely on the 80% block. The remaining 20% is withheld as a blind exam. The machine applies its newly generated logic to this unseen data and produces a concrete error rate. That error rate is known as the cost function. The entire goal of the model from that point forward is to run countless iterations, constantly updating its internal weights to push that cost function as close to zero as possible. Deliberately hiding part of the data from the machine forces it to understand the underlying patterns. That is the exact moment an AI demonstrates true predictive intelligence. For the past decade, these predictive models have been mostly passive. You ask a question, and they output a response. Today, we are deploying active, autonomous systems that can execute complete workflows on their own. This peak expression of the AI blueprint is known as an AI agent. An agent operates with three core components. The first is its brain. In the center of this diagram, a large language model acts as the logic hub, giving the agent the ability to reason, plan, and break a complex request into manageable steps. Next is memory. A continuous data loop feeds historical context back into the central hub. By retaining the context of past interactions, the agent practices metacognition, analyzing its own reasoning to correct errors and improve its accuracy over time. Finally, it has tools. Through API connections, the agent can reach outside of its own programming to physically execute tasks, like querying a live database, checking a calendar, or running a block of Python code. The integration of reasoning, memory, and tools provides the system with the capacity to execute multi-step tasks without human oversight. These individual workers are now being linked together. Developers are orchestrating entire multi-agent workflows designed to solve multi-step problems with zero human intervention. In this setup, a planner agent might draft a strategy, pass it to an executor agent to write the code, and hand the result to a validator agent to test it. They pass their work back and forth, verifying the logic until the final output is finalized. As these systems gain the ability to initiate their own actions, the need for governance and alignment protocols becomes a technical requirement. We must ensure that the software managing these execution loops remains tethered to human intent. We are shifting from an era of simple queries to one of coordinated execution, where the blueprint of AI continues to expand into every layer of our digital infrastructure.
Watch till the end? You'll love what's next. Subscribe, like, and comment for more amazing insights.